Right. All right. So hello, everyone. My name is Donggi, and today I'd like to give a presentation about addressing a non-station challenge in the multi-station reinforcement learning. All right. So the multi-station reinforcement learning, it has the fundamental problem, which is about the non-stationarity. This is happening because there are a lot of agents are simultaneously learning. So in here, I'm providing an example, such as playing soccer. So let's say you're actually losing after the first half. So since you're losing, you're likely to be more offensive in the second half. If you're actually winning after the first half, it's likely that you'll be doing the defensive strategy. So how you're actually changing this strategy in multi-agent learning, you're changing based on your underlying learning process or your underlying learning algorithm. So the question I'm trying to answer here is that is it possible to consider the learning of others and adapt to their non-station policies, which becomes the objective of this presentation. So can you do a efficient adaptation by considering the learning algorithms of the others? But there are challenges I have to answer, such that how to design a new value function that considers the learning of the other agents, and also how to infer the hidden learning dynamics because this underlying learning dynamics would be actually hidden to the other agents. And also there will be actually inherent uncertainty. So how can you actually incorporate this into a new value function? The key ideas I'm trying to convey here is that I'm providing this learning awareness value function. And I'm also using this approximate variation inference to be able to predict the underlying learning dynamics of the others. And also I'd like to propose a base adaptive stochastic game that considers the exploration and exploitation trade-off with respect to the uncertainty about the other agents, the hidden learning dynamics. All right, so going to the first question, how to design a new value function that considers the learning of other agents. And here I'm comparing the two value functions. The first one is the station value function that's used in the MADDPG paper. And there's a learning awareness value function that I'm trying to compare to. And the station value function is the one where the future actions are actually sampled from the current policy parameters, as you see on the left figure. But this is incorrect because it assumes that the others have fixed policies in the future, and because other agents are learning, they will actually have different policies in the future. So the learning awareness value function is actually accounting for this and saying that the future actions will be sampled from the future policy parameters of the others, and how the other agent will be evolving is going to be based on their learning dynamics or their underlying learning algorithm also. So is it useful to consider this learning awareness value function? The answer is yes. In here, I'm showing this stateless zero-sum game where this game has a Nash equilibrium at the origin. The nice part about the learning awareness value function is that as you consider the learning awareness, you can actually converge to the Nash equilibrium. But if you do the station value function, then you actually get the divergence of the performance, which turns out to be really not a good thing to do. So the caveat here is that I assumed access to actually the true learning dynamics of the others so that I can actually analytically compute the gradient, whether it's stationary or the learning awareness value function. But in practice, it is actually not possible to get this true learning dynamics. So can you actually infer this hidden learning dynamics? So for this direction, I've used the variation inference so that I can actually predict this U minus I given this optimization. So I'm showing here that by using the variation inference, it is actually possible to predict the infer U minus I so that I can actually predict upon the next update policy. The really nice thing about this plot is that as the agent sees more data about how the other agents are evolving over time, the difference, the ground truth is actually becoming to very smaller difference, meaning that it can actually predict very accurate. At the same time, the uncertainty, which is the radius of the circle, is also decreasing over time as you see more data, which is a very good thing to get. Also, I can use the same technique to predict not only the next update policy, but actually next maybe 20 update policies, and the difference is also very tiny too. So lastly is that since we saw this uncertainty that's associated with the this inference, can you actually use this in the learning awareness value function? So I've also studied this Bayesian theory where each agent is maintaining its belief of the peer's current poses and the learning dynamics, and the agent is making a decision based on this hyperstate. So that this hyperstate includes not only the state but also the belief about it. and you actually have the belief update. So the nice thing about this base adaptive learning OS field function is that the agent is inherently thinking about the uncertainty and thinking about that in making a decision when doing so to improve its expected return. So in summary, I provide a various methods, or actually the one story to addressing non-staging challenge. But to do so, I've introduced learning OS value function. I also applied the various inference so that I can actually predict the hidden learning dynamics. Also, I studied the base adaptive stochastic scheme so that we can principally incorporate uncertainty into the learning OS value function. So that will be the end. Any question? I have to happy to answer.
Thanks, Dongchi. So one question I have is, so when you're learning to predict how other agents evolve or their learning dynamics evolves in the future, so you must be doing this in hindsight, right? That you assume you have access to their learning in the future, and then you come back some time steps, and then you forecast how the learning dynamics is going. So you convert that into a supervised learning problem?
It's a great question. I'm actually doing a forward view in a sense that given the trajectory that I have seen up to the time step t, because that actually encodes how the other agents have evolved. So that once I actually have the similar to how when you have the state transition, I can actually do the simulation. Similarly, if I have actually access to the UMass I by the predict or the inference, I can actually do a simulation into the future. So that was the technique that I used.
Okay.
Thank you.
Any other questions? Any other questions from anyone? No? So, well, let's thank Dongchi once more, and let's move to the next presentation.
Okay.
Andrea, we can't hear you.
Can you guys hear me now?
Yes.
Okay, sorry for the problem. So, hi, my name is Andrea, and today I'm presenting my work about robust and sample efficiency compression of a tube MPC policy via imitation learning. So, as we all know, MPC is a very popular tool for control of complex robotic systems, but is computationally expensive. So one of the approaches that is gaining popularity is to address these computational issues is to compress the MPC policy obtained by solving an optimization problem into a computationally efficient representation like a neural network using techniques like imitation learning, in which the MPC acts as a demonstrator and the neural network is trained with the demonstration collected from the MPC. However, I would like to highlight one issue, which is that imitation may fail due to the extra covariance shifts caused by the scene-to-real gap when transferring the policy trained in a simulated environment to the real world, or by disturbances encountered by the system in the real world. Model error or disturbances can in fact change the state distribution of the system encountered by the system and push it to areas where the demonstration may have not been collected, causing the failure of the system. So in my work, I would like to try to address this problem. Specifically, I try to understand how we can increase robustness to these distribution shifts by leveraging the privileged information extracted from the expert, which is a robust tube MPC, so a model predictive controller which acts in a robust way. So one of the approaches commonly used in the literature to address these challenges is based on domain randomization, which consists in applying a variety of model parameters and disturbances during the training phase. This approach can be, however, impractical, especially if we are trying to train on a real system. It is hard to apply all the possible disturbances that the system may encounter. So we instead propose to leverage the privileged information from the robust tube MPC and specifically leverage the fact that the expert contains a model which is called the tube Z of all the possible states where the system may end up due to the model disturbances. Additionally, the expert contains knowledge of which action should be taken in those, let's say, bad states to bring the system back to the nominal reference trajectory and counteract the disturbances. And specifically, we would like to investigate how we can embed this knowledge into the Dagger, by sampling extra states from the tube and the corresponding action and adding those to the training dataset used in Dagger. So the changes in the algorithm are highlighted in blue and just highlight the fact that we want to sample extra states from the tube and add them to the training dataset and train Dagger using this additional information. In this work, we evaluate two different strategies to sample extra states from the tube. One, which we call dense, which samples more states, but scales poorly in state size exponentially. And one, which is instead sparse, which samples less states, but scales nicely. The evaluation is performed in with respect to a trajectory tracking task, where we have a quadcopter who has to follow an 8-shape trajectory, you can see here, and in blue is the performance of the expert. We consider success if the robot manages to stay in the air without crashing in the wall or in the floor. We first evaluate the performance of the expert and of baseline approaches as a function of the number of demonstrations used for training, and we evaluate their success rate. The results show that first, the expert, the blue line, achieves 100% success rate as expected in the source environment, so an environment which is the same as the training environment. And similarly, baseline based on Dagger and domain randomization achieve 100% success rate in about 5 steps. Our approach instead reaches full success in just a single step. We then transfer the proposed strategies into an environment which presents strong wind-like disturbances, which push the distribution of the states encountered by the system to something different than what's seen in the training domain. As we can see, the expert still achieves almost full success rate, while Dagger and Dagger plus domain randomization struggle to converge. Our approach in both the different sampling strategy achieve 100% success rate. We then look at the performance in terms of trajectory tracking error in the source domain, and in the target domain. The results show that all the approaches achieve similar performance to the expert in the source domain, while in the target domain, the one with disturbances, our approach has lower tracking error than the approach based on Dagger or Dagger plus domain randomization. And last, we conclude by just showing how the compressed policy performs in a high fidelity simulation. And we also observe that the computational complexity has been reduced by almost 2 orders of magnitudes, with inference time going from 50 milliseconds to 0.2. So in conclusion, we have shown that leveraging expert knowledge by sampling augmentation in Dagger can transfer the robustness properties of the expert, achieving greater sample efficiency. And in the future, we would like to quantify potentially how much covariate shift we can cancel in a theoretical way, and also test on different environments. So yeah, thank you. I'm happy to take any questions.
Thanks, Sam. Are there any questions from anyone?
So in domain randomization, we are basically like uniformly sampling the parameters or randomizing the parameters. And here you are saying we can just learn from a robust tube. And how do you know that that tube range is enough? Like it covers the real system?
Yeah, I assume knowledge of the worst case disturbances that we can encounter. So the tube contains a model of the possible disturbances, and I assume that that model is correct. So in the real world, we do encounter that type of disturbances. And I use the same model also for domain randomization. So the disturbances are just forces of magnitude between 0.1 to 0.3 newtons, and those are also used in the domain randomization phase.
And how significant is the improvement, like in the results slide? Like the number, what do they mean? Like 3,000, 4,000?
Oh, in the trajectory tracking error. Well, it's just somehow the distance, the average distance between the reference and the trajectory. But
Unfortunately, Andy, I'll have to stop because we're running short on time today. So maybe you can discuss this question offline if Tao has the question.
Yeah.
So
sure.
But thanks a lot. Let's thanks Andrea and let's move to the next presentation.
Okay. Hi everyone, can everyone see my screen?
Yeah.
Yep. Okay. So good morning. I will be talking about how we can improve smooth control in model-free reinforcement learning. So basically, we know many success stories of model-free reinforcement learning for robotics application, specifically locomotion, right? But if we look in more detail in the outcome policies, in most cases, we can see that the policies are actually jerky and have like weird movements that in the real world can damage actuators. So this is something that, especially if we consider that the real world has other problems such as non-stationarity and sometimes highly stochastic environments, this is actually even worse for our robots. So in this project, the goal was to investigate if changes to the policy or the policy outcomes could help mitigate this problem. So what I did was compare 6 different strategies to reduce the policy jerkiness. So we start from these, the typical reinforcement learning framework, an environment, and an agent with policy. So I started from a baseline that was with a core of an MLP policy. I also tried a recurrent neural network-based policy, specifically a GRU. Then I tried other strategies that were a bit more creative. So for instance, one took the action, the outcome of the policy and used this as input in the next time step. Another approach was instead of just outputting the action of the policy, have a kind of a jerkiness controller that takes this action and might change it a bit in favoring smoothness in the process. So one approach this controller can do is instead of just outputting the action, output the action difference, so have the policy compute the action difference between 2 consecutive time steps. Another approach I tried for this jerkiness controller was outputting the moving average across different multiple time steps within a window M of size M. And then if you take into account the reward, another approach that we could also do was modify that reward via reward shaping to account for the jerkiness in the environment and kind of penalize that jerkiness, right? So this 6th approach could be regarded as an additional process or additional tool we could use in each of these strategies. So I focused on PyBullet's environments, which consist of 4 locomotion tasks with different number of joints. Basically, in these environments, the state corresponds to different sensors about position, velocity, roll pitch, and then we also have specific sensors in each of the joints. The action is basically the torque that at the time step the agent actuates on each of the joints. And the reward is a linear combination of 4 different objectives, basically just being alive, traveling as much distance as possible, and then there's penalization for the electricity and the strain in the joints. So in each of the environments, I also implemented a way to compute the jerk in both in the body and the joints and kind of consider them separately. And the goal was to reduce during an episode the maximum value of the jerk observed for both the body and the joints. In the case of the reward shaping, that those values were also added as a penalization in the reward. So the results were not as promising as I expected. So first of all, one of the main conclusions that reward shaping, at least in the way I have implemented, is not as helpful. I've seen that this is very hard to tune and depends a lot on the environment. So here first I'm showing the evolution of the return, the jerk in the body and the jerk in the joints for the specific case of the humanoid without reward shaping. So I'm comparing the 5 strategies that I talked about before. And if we cannot show these results for each of the 5 seeds, and we plot the return against the jerk in each of the for these environments with separate body and joint, we can see that reward shaping is actually not useful. So it's even not able to reduce jerk. I mean, I've seen this is hard to tune. And then other strategies, when we specifically use the moving average, we are able to reduce the jerk while maintaining the reward. So the moving average strategy was probably the most robust one, and it is specifically very robust when we use reward shaping. But when we use reward shaping, we're actually not doing that good in terms of locomotion on the task. So I wouldn't consider this as a meaningful insight. But in any case, these results are very dependent on the environment. So there's no clear method dominance, because if we kind of now plot the same thing on the hopper and the ant, the plots look completely different, and the relationships are different, right? So for instance, in the hopper one, the action difference policy was able to reduce the jerk in the joints while kind of keeping a bit of the return, but then if you kind of look in the ant environment, it did completely, it didn't perform the task at all, right? It basically stayed in the same place, and the jerk is high. So on another difference is that, for instance, the baseline policy is actually good it dominates other strategies in the hopper one, but in the ant one it doesn't, right? So basically, as future work in this task is tune reward shaping, kind of try to study more why and when it is helpful. Maybe instead of just using the same coefficients, try to do some dynamic strategy. A method that generalizes well across environments would be desirable. And maybe we could also look into other types of tasks, such as manipulation. Thank you very much.
So one quick question, did you try changing the entropy coefficient and how that relates with the jerk?
The entropy, I didn't use entropy coefficient. Oh, I trained them with PPO, and I didn't use the entropy coefficient in the loss function.
I see. Okay, so I mean, this training was without entropy at all, is what you're saying? This is just PPO without entropy.
Yeah, PPO without entropy. Yeah.
I see. Okay. Thanks, Joan, and let's move on to the next presentation.
Can you all see my screen?
Yeah.
All right. So this is a neural net. We all love neural nets because given a feature vector, we can predict whether somebody has an illness or what a user might rate a song. And in this class specifically, we've looked at neural nets in these deep reinforcement learning algorithms, and we've seen how we can train agents with them. However, for temporal data, a simple feed-forward neural net might not be able to capture all of the temporal nature of the data. So today, Anubhav and I will be talking about recurrent deep reinforcement learning with applications to financial trading.
Great. So our main problem statement is that we're going to try to trade a portfolio of a small number of stocks and hopefully beat kind of the average returns of those stocks or the individual returns and gain some edge or value out of those. And the assumptions are we trade once per day at market open. The trade friction is kind of low and that we can trade arbitrarily fractional shares. And the goal, maybe contrary to some reinforcement learning problems, is kind of really easy and simple to frame for this problem. We just want to maximize kind of our net return. So like maximize day to day the amount that our account value goes up. And observations are going to be compiled purely from price histories of the equities included in the portfolio. So there's no kind of data from stocks and equities that aren't inside of the portfolio. And there's no kind of like market sentiment or news scrapers that are involved in aggregating the observations. So this is generally like a hard problem. Really, the market is influenced by the huge state of the world that includes kind of, human psychology, like market events, news. It's kind of hard to capture all of that. It's non-stationary. The things are changing. There's this kind of distributional shift every day. There's a high signal to noise ratio, and you have these kind of like really rare events that can happen. So for example, COVID in last year and how that affected the market and still affecting the market to this day. So we construct a stock trading environment that starts with scraping data from Yahoo Finance API. And then we kind of take the approach that was done in the Google Loon project where we didn't actually have enough data to train on. So we then took that data, perturbed it, and to kind of pad our data set, and then also kind of incorporate technical indicators like moving averages to form the observations. So taking all of that data, we then kind of train the PPO agent using recurrent policy, and then eventually test and validate on kind of held out test data that was held out from the Yahoo Finance real stock data. Yeah.
So talking about the neural architectures, we constructed a recurrent architecture for our agent. And so here, these are the observations, the time series observations, and they go into gated recurrent units. And the number of layers is user determined. And we take the last output as our H-dimensional intermediate output to input into this simple feed-forward head to get an output for the actor or the critic. Now, as a baseline, we also wanted to compare it to a feed-forward network and to see how the two would perform next to each other. So once again, we have our observations that just go into a fully connected network with n layers. It spits out an H-dimensional output that we once again put into the same feed-forward head. Now, as a sanity check, we first wanted to try this on the cart pool. And this is just the cart pool that we've seen before in one of our P sets. And the traditional observations that we had were the position of the cart pole and then the velocity. However, because we're studying temporal data in our project, we decided to instead remove the velocity and only include the position for the last 3 states. Now for the results over here, we have a single layer of GRU or fully connected units, and then here a double layer. So in both architectures, you can see that the recurrent in blue actually outperforms the traditional feed-forward architecture in red. And as another example, we also tried this on the half cheetah. So in the half cheetah, you have the position of the cheetah and then the angle of the 6 joints, as well as the velocities for those. Once again, we removed the velocities and only included the position for the last 3 states. And here again, we see that for the single layer and double layer, both the recurrent actor critic architecture in blue outperforms the feed forward in red.
So based on that kind of exploratory study of recurrent versus feed forward architectures, we decided to go with the recurrent architectures for the financial trading problem, given the kind of temporal correlations and nature of the data. Kind of skipping over a lot of details here, of course, but ultimately we found that the recurrent agent could actually perform quite well, although we'll see that it was a mixed bag of results. But in this case, we trained from data from 2000 to 2017, and then we tested it on data past that point. So here we're showing data that, for year-long trading periods that started between 2017 and 2019. So going from 2018 to 2020 before the COVID market crash. And we see that the agent actually does really well, beating the average kind of buy and hold strategy by almost 7 points annualized. So that's a really good result. But if we go on to the next slide, so this is kind of the year involving the market crash of COVID and kind of the subsequent turbulence and volatility. And we see that the agent actually performs the worst, much worse than any other stock or equity in the portfolio. And we kind of suspect that this is due to the really, the previous slide was showing the kind of great bull market. Things were just going up. And here we have a lot of up and downs, a lot of kind of market crashes and recoveries, a lot of volatility and different equities moving oddly. So we suspect that that caused the agent to kind of not be able to generalize properly to this time period. We go to the next slide, kind of demonstrating the market recovery. We see that the agent is certainly not the worst, but it doesn't have that kind of superlative performance that we saw on the first slide. And again, we suspect that one cause of this is that we're still going through a weird market. There's a lot of kind of injections from the government that stocks are behaving weirdly. And we're still recovering from COVID and the market that was caused by that. Another hypothesis is that we're just getting further and further in time from the training data. Yeah.
We have like 10 to 15 seconds to wrap up.
Okay, gotcha. Yeah, so in the interest of time, I'll just leave this up here. But one thing that we want to test in the future is kind of a more online strategy where as new data comes in, we're continuously training. Yeah.
Any quick questions?
Yeah, I'm curious, how did you select the basket of stocks to like train the agent over and let it select?
Yeah, so right, so these are all really kind of liquid, high market cap S&P stocks. You'll notice that, so these are some of the biggest in the S&P, but we specifically excluded tech stocks because our training data kind of was from 2000 to 2017. So if you pick like Apple, for example, the a really locally optimal solution is just to buy and hold Apple and never like trade any other stock, and you'll like beat the portfolio like by a huge margin. So I mean, that's not the globally optimal solution, but it's really like locally optimal, and it's hard to get out of that. So these are all stocks that basically experience similar returns over that 17-year trading period. But we're still like liquid enough that we can make these assumptions about low friction and things like that.
Cool. So I think that's all the time we have. So thanks, Kylie and Anubhav. Let's move to the next presentation.
Okay, yeah, I'll start sharing my screen. Can you guys see my screen? Yeah?
Yes.
Yeah, okay, cool. I'll get started. Hi, my name is Jeremy, and today I'll be talking about my project on more like a case study of using GNN to train a neural network policy for for multi-agent information gathering task. Okay, so here's some brief overview and the problem setup. So what is information gathering? So the task is really about how to plan trajectories for robots in order to make kind of valuable measurements about the uncertain processes in the environment. And in the pictures, we can see that there are many different applications, for example, ocean temperature monitoring, environmental monitoring, search and rescue, and so on. Right, and by having a lot of robots, we can do such kind of tasks more efficiently. And there's some related work in this area. For example, there's model-based methods that it's more like a model predictive control kind of method that you grow a search tree and you pick actions that minimizes the uncertainty over long horizon. In terms of multi-agent reinforcement learning, there has been a lot of work in terms of kind of training scalable policies across agents. And a really commonly used method is to have a decentralized actor or even shared actor for homogeneous agents. And usually there's a centralized critic to help the training process that has access to the global information. And here, what we're really interested in is to see if we can train a policy that generalizes to different numbers of agents, and also it doesn't require retraining when the number of target estimation targets vary, which changes the which can potentially change the input size for a traditional learning-based method. So here's a brief overview of the environment. So we consider a simple case where we have some landmarks, uncertain landmarks to estimate, shown in red, with some initial beliefs shown in green. And we make some simplifying assumptions on the target dynamics. For example, it follows linear dynamics with Gaussian noise. We do a centralized estimation, and the robots don't have localization uncertainties with finite choice of actions. And they're homogeneous with a limited field of view. As an overview, our focus is really to try to learn a policy for the agents, and all the estimation part and the target dynamics are extracted as part of the environment. As for the method that we use, I try to use a GNN-based policy from this paper. And the general idea is when we have different number of entities to estimate in the environment, one way to encode that into a single vector is to use the so-called scaled dot product attention method, where after we transform the initial belief about the targets into hidden space, we can use this attention method to produce a fixed size embedding. Then we feed that and concatenate it with robot's own embedding. So in this case, robot
each robot has its own policy, so it takes its own local measurement, convert it into embedding, and concatenate it with the environmental embedding. After that, we do message passing across all the agents for 3 times. Then the eventual output is fed into a value network and a policy network to generate control actions for the robot. In terms of training, because the method generalizes to different numbers of agents and landmarks, so we just used 2 agents and 3 landmarks. We use PPO with entropy regularization. Each rollout has 100 steps over time, and each update has 32 rollouts. And here we see the policy converges in 3 hours on my computer. And here's just an example of what the policy ends up looking like in the test scenario. And we can see that the uncertainty reduces. In terms of the generalization results, I looked at 2 cases. One is I fixed the number of landmarks and vary the number of agents. And I fixed the number of agents and vary the number of landmarks. And we compare it to 2 methods. One is purely random approach, which is shown in blue. And there's a search-based method that's suboptimal. And the agents, they don't collaborate with each other. So it's fully decentralized. And we can see, well, the GNN policy doesn't outperform the method, but it generalizes well to different numbers of agents and landmarks. And it closely follows the search-based method. Right, my conjecture is that the model-based method has an advantage since the model is very accurate. In this case, it's just static landmark. Right. So what is wrong with the GNN policy? Because my guess is that with the graph context, kind of using GNN, it has a strong inductive bias in terms of like what the problem structure is. And we can see that if we only have 1 agent and we vary the number of landmarks, actually our GNN policy follows very closely with the search-based method. So it actually learns well like a single agent policy, but it doesn't lead to collaborations across the agents. And as visualization, we can see for a search-based method, the agents, their policies are less correlated. So sometimes the agents split off and take measurements that are less correlated with the measurements from the other agents. But if we see the deployment of GNN policy in this case, we can see they have this highly correlated pattern. Therefore, they take really correlated measurement, which is bad for estimation purposes. Right, so as future work, I think I want to look into how to kind of encourage more collaborations using GNN so that agents actually take less correlated measurements for estimation purposes. And in my current work, I'm not using LSTM, but potentially using LSTM can improve the performance. And since we have this suboptimal policy, we can maybe use imitation learning to pre-train the policy. Maybe that will help the learning purposes. But yeah, of course, in harder scenarios to consider. Yeah, with that, I'm happy to take any questions.
Any questions from anyone? No. So Jeremy, it was not working 2 days ago. What happened? Did you find the bug?
Yeah, so it wasn't a bug. It was just really like, so the issue I had was that the training actually doesn't converge and it collapsed and it's super noisy. It turns out that I didn't normalize the input properly. So like there's this one input that's much larger than the other ones. Then it leads to like huge gradient in the network. But at the same time, I'm thresholding the gradient steps. So it's like we're choking part of the network and not letting it learn. So I think that's the main issue. Yeah.
Okay. Well, thanks, Jeremy. And looking forward to your project report. Let's move to the next presentation.
Thanks.
Hi, can everyone hear me? Okay. Oh shit.
Hi everyone. I'm Xiaozhong Jiang. My teammate is Steven Yang. So our project is investigation and preliminary implementation of multi-agent reinforcement learning. We have spent the whole semester learning some reinforcement learning techniques. However, in real world, it is a more realistic scenarios that multi-agents are involved. So it is very important to extend single agent RL algorithms to multi-agent problems. The relationship between the agents can be simple, such as collaboration and computations, or it can also be a mixture so that the design is challenging and interesting. So here are some common MARL algorithms. This algorithm can be categorized into two categories. So the first category is called independent learning, where all the agents learn independently and treat other agents as environment, such as IDQN, IA2C, and IDDPG. However, a big problem of such method is stability because the environment is always changing. Another category is called centralized training, decentralized execution. So during training, all the networks are trained using shared information from different agents. However, in the execution period, each agent only depends on its own observation so that the execution is decentralized. So some algorithms in this category are value decomposition network, QMix, central V, COMA, and MADDPG. We first tried to implement central V and independent Q-learning in the environment called multi-robot warehouse environment. However, we failed to get any workload policy and the networks are rarely updated. And we found that the reward of the environment is too sparse. As it is shown here, the reward is assigned only when the agent reached the goal location with the requested shelf. And the state space and action space is pretty large, not to mention for multi-agent to explore. So we switched to another environment developed called multi-agent particle environment. So in this environment, we choose the task called cooperative communication. This task consists of two cooperative agents, a speaker and a listener. So at each episode, the listener must navigate to a landmark of a particular color and obtains reward based on its distance to the correct landmark. However, the listener can observe the relative position and color of the landmarks. It does not know which landmark it must navigate to. Conversely, the speaker's observation consists of correct landmark color, and it can produce a communication output. Thus, the speaker must learn to output the landmark color. Although this problem is relatively simple, as we show later, it poses a significant challenge to independent learning algorithms.
So for the simpler multi-agent environment, we basically applied two algorithms just for a direct comparison. We adopted the independent and DDPG on the independent category, and we also adopted the MADDPG, which uses centralized training while decentralized in action. So on the left image is the architecture for the DDPG, and on the right is for the image for the MADDPG. You can see basically the two architectures are really similar, except for the fact that the MADDPG adopts a joint critic network and a joint replay buffer, and in the DDPG one, we are very familiar that those are separated. Next slide, please. So here is our results from training by training with these agents in our environment. On the left is our training with the DDPG agent, and on the right is our training result visualized for the MADDPG agent. And for the DDPG agent, we can see that the listener barely reaches the target state. Sometimes it reaches a goal that is in a different color. And sometimes we observe that most of the time it just basically goes to a random location, which is kind of really fairly apart from each of these landmarks. We also observe that the trajectory is rather vibratory. Instead, when we observe the trajectory generated by the MADDPG agents, we can see that as iterations goes by, most of the time the listener is able to reach or at least approach the targeted goal very well with a trajectory that is a lot smoother than the one trained by the DDPG agents. Next slide, please. And more quantitatively, you'll compare the rewards, value function laws for both agents and policy laws. And we can see that indeed the MADDPG agents intrinsically utilize the coordination between between the two different agents better, and it is able to achieve a higher reward and reduce the loss function in both cases. Next slide, please. And we also used some metrics to evaluate the robustness of the two algorithms. Mainly, we use dispersion across time and short-term risk across time. And we can see that the MADPG agent doesn't necessarily imply improvement in robustness. So this is something we are really looking forward to see in the future. And next slide, please. For our conclusion, we studied and briefly summarized multiple MARL algorithms, among which we apply DDPG and MADDPG on the MPE environment. And we do see that the MADDPG agents performs better in terms of reward, and the actual behavior is more natural and more smoother. The MADDPG coordinates better between the listener and the speaker. However, we observe from the metric that we use that the MADDPG agent doesn't imply a robustness improvement. There are some other findings during our application of the robotic warehouse that the complexity of the environment has a significant impact on the actual deployment of the RL algorithms, especially when there are multiple agents exist, and the state variables can extremely complex of the environment. And for our future work, we want to investigate more thoroughly on different MARL algorithms. We want to investigate possible causes of the robustness, eccentricity in MADDPG. Thank you.
So I don't think we have any time for questions. So we will move ahead, but thanks a lot for your presentation. So let's go to the next team.
Hi. Hi, I'm Sean, and today Raphael and Pedro will be discussing the work we did in terms of exploring the whole chess scene, and more specifically exploring the limits of implement a lean agent for chess, so something that is a smaller framework and has less trainable parameters. And so just to recap, I mean, AlphaZero is one of the greatest achievements in like human AI. And so you're starting from supervised learning and reinforcement learning to just pure reinforcement learning. We were obviously, this is one of the main reasons why we took this class. We really wanted to kind of look at exploring this whole chess game using reinforcement learning. And so this was our main motivation for the project. But the thing with AlphaZero is that it took $25 million to train and to create a competent, or like one of the best chess agents out there. So we thought it was kind of crazy that it took so much money. So we wanted to really explore how we could do this for less computational power and perhaps with a smaller framework. So that's what we mean by lean. So we're trying to explore it all for a smaller framework. So starting out from this, we did like DDQNs, and also we moved on to MCTS later on, and then also implemented some demonstration learning to try and push our model forward to be better at chess. So when we started out with capture chess because which is like a simpler framework for chess. It's just the goal of this type of game is just to capture pieces and not to checkmate. So the potential reward you have to seek is a lot easier and short term. And so we started out with just DDQNs and just like vanilla DDQNs, which are trained against a random agent for 500 games. And then also we went on to train a second type of agent for capture chess, which is self-play DDQN, where essentially we just trained the DDQN against vanilla DDQN. And so you can see like on the right-hand side, on the x-axis is the turn count for a game in all the testing games, and on the y-axis is the material advantage. So the blue line shows vanilla DDQN, and that has the highest material advantage. It plays very aggressively in games, and self-play does well also, but has a smaller material advantage. But when playing the two against each other, we see that self-play actually beats vanilla DDQN, showing that it's more robust against different kinds of opponents. Yeah. And this is all with 18 trainable parameters. So it was quite interesting to see good performance.
Yeah, I'll hop on real quick. Yeah. So we transitioned to real chess where we modify the network to include both a value hit and a policy hit. The value hit outputs a single value that represents the advantage of that board state, and the value hit outputs the Q values that represent the relative strength of each possible move. In real chess, we face the sparse reward question and hope to answer this question in the next slide. Next slide. Yeah, so to overcome the sparse reward challenge, we implement MCTS. The MCTS works like a minimax tree search that does not explore all the possible children, but uses outputs from the value hit to determine which are the most promising search paths. If we were to search all the possible paths for each chess move, we'd quickly approach intractable time complexities for our resource limits. So we enforce a number of simulations to 100 per search move, just so that we can expedite training. And in our chess scenario, we use UCB scores to select paths to explore. This way, we balance exploration and exploitation while training our agent. Next slide. Our lean agent with one-layer CNNs show promise in low training environments. We experiment with different number of CNN layers for our DDQN agent and observe that the leanest agent had the gentlest learning curve and began to actually achieve wins shortly after training began. From the example game on the right, you'll probably see a bunch of amateur blunders, but after only 120 games of training, we note that the agent has learned how to checkmate. We report a 10.2% checkmate rate and less than 1% loss rate against a random agent. Notably, the time to train now is about 95 seconds per game. Next slide. So we tried to expedite the training process by introducing demonstration learning. We fitted 2 valuation networks to substitute the value hit of our DDQN to help warm start the training process. Remarkably, the demonstration learning leads to early peaks in training, but this eventually drops off probably due to the learning rate, leading the loss towards another local minimum. We believe that more training games would more accurately show the value of demonstration learning. However, we do report good results for this semi-supervised agent with a 15.3% checkmate rate against a random agent. Next slide. Yeah, so to conclude, DeepMind people are truly mega minds. We had a lot on our plate over the past 3 months, trying to build from scratch a lighter version of their AlphaZero algorithm. We believe we made great headway, but we are also humbled by the many ways to improve this project upon. Computational complexity was definitely the biggest challenge, so we restrict our findings to understanding learning dynamics in lower training environments. Further work should apply sparse CNNs to better handle the sparse checkmate reward and encourage more meaningful training cycles. So to recap, we find that lean architectures have the potential to support a DDQN in learning viable chess strategies from a MCTS algorithm. Based on all of our experiments, we determine minimal CNN layers, Poisson laws to magnify policy loss, an adaptive learning rate, and a unified value and policy network work best in lower training environments. So with that, thank you everyone, and happy to take any questions.
Any questions from anyone? So one question I have is, so why do you think the self-play DQN performs worse in the vanilla DQN against the random agent?
Mm-hmm. Yeah, Sean, you want to take that and add that slide?
Yeah. So we think that because the self-play was trained against vanilla, it becomes more defensive because vanilla DDQN plays very aggressively. And if self-play wanted to beat vanilla DDQN, it had to learn to be more like defensive against its aggressive moves. And then consequently, it's unable to capture as much because it's more defensive.
Yeah, and if I were to quickly add, we actually tried to switch up the agents to introduce like some stochasticity to the opponents at every certain time intervals, just so that our agent is learning to play against a robust set of opponents. But we observed that probably due to the learning rate or the shallowness of the CNNs, it starts to overfit to each agent. And we suppose that a lot more training games are required against each time step of an opponent for the CNN to actually be able to be robust. So in our case, we really need to be able to scale up to more training games.
Okay, thank you.
Thank you.
So let's move to the next presentation.
All right. I think my partner fell asleep, but I will do my best. All right. Hello, everyone. I'm Isaac. I'm worked on this project with Serge, and we'll be presenting about side tuning, a novel approach to network adaptation. So generalized learning can often be approached sequentially. If you have a task, you can learn additional tasks in a sequential manner. But two problems arise here, which are catastrophic forgetting or rigidity. And if you remember, catastrophic forgetting is if you have an agent trained on an original task and it now trains on a new task, it may learn that new task, but now forget something about, it might like over bias to that new task and forget stuff about the original. And then similarly, rigidity is the opposite of this, where the previous training of the network actually biases it and prevents it from learning new tasks as well as it could have. Side tuning offers a new method for network adaptation. So as I said, current approaches to this sequential or generalization, you can do things such as doing a pre-trained fixed feature extractor that allows you to, learn features on very broad set of environments and then have your agent use that to learn the task. You can also fine tune an agent using using a previous network, but this suffers from the problems I described. Side tuning takes an additive approach using a side network. So it does this via having the original network that's already been trained and holding the weights frozen, and then adding a new network that you just add to provide the new information needed for just this additional task. And it does this via alpha blending by a weighted combination of these. And the idea is that because the original network is fixed and you don't change it during this new training, you're not going to suffer from this catastrophic forgetting since you can handle the original task just as well. So for this project, we chose to use the mini grid environment. And if you remember, it has a variety of different tasks with different levels of difficulty. And they're generally sparse reward tasks. We decided to focus on some of the easier approaches so that we could really just focus on analyzing the different ways of implementing the side tuning. So we chose empty of different sizes, the unlock environment, which has a key and a door, as well as the door key, which has door key, but then also a goal after that door. And so the first thing we wanted to do was find basically scenarios where we see this catastrophic forgetting appear. And you don't need to look at all the results here, but what we did is we trained an agent from scratch on these different environments, and then evaluated each of those agents on each of the other environments. And what we'll focus on here are just the empty 5x5 and unlock. And in particular, what we see is that the agents, as expected, when tested on the environment they were trained on, perform well at these 0.94s respectively. But when they're evaluated on these corresponding other environments that they were not trained on, they do not perform as well, which is also expected. And traditionally, we could do fine tuning to maybe improve this performance, in which we tried. And what we see is that the 5x5 agent then performs better on the unlock environment, but we actually see a decrease in performance in this empty 5x5, basically in the original task the agent learned. And it's not a very extreme forgetting, but it is significant and something we want to look at for side tuning. So what we attempted was side tuning with different alpha parameters, basically the weight of using the previous network versus the weight of the new network that we're adding to it. And what we found is that the alpha equals 0.05 actually gave the best performance and helped us prevent a lot of the loss we saw with the fine tuning method. And this alpha parameter could be learned as a parameter in the network, but we didn't have time to get that working for this project yet. We also looked at how different model architectures would affect the side tuning. And the idea with side tuning in general is that you have a lot of small networks for a task rather than having to train a whole new large network each time. So our original test was on the same base network as using a side tuning network that was the same as the base network. But we also tried a medium-sized MLP and a smaller MLP. And what we actually saw is that the larger network performed the best, and the smaller MLPs did not perform as well. This was a little, I mean, it's expected, but it was a little underwhelming that the smaller networks did not perform as well, given that we'd expect sine tuning to be able to handle these small changes in these relatively easy environments. So overall, for the paper, we're also looking at sample efficiency, because as I said, the goal of side tuning is to be able to adapt to these new tasks efficiently and quickly. But we also want to explore more complex scenarios and more dense reward scenarios, which may be better suited for seeing the impacts of this side tuning. Thank you.
So did you have to tune the alpha parameter depending on the environments?
So we basically we kind of did a parameter search on the different environments, and this was for these specific ones. This is what we found. But we have been trying to get the like actual learning of that parameter to work, because that seems like kind of a key ability that would allow it to adapt more easily.
I see. Okay. Seems like there's a question on the chat. So what is the size of the side network with respect to the reference network?
Yeah, so that's actually what we found here is, so the paper, the original paper, they start with, they suggest like a similar network to the reference network, which is what this is, basically the same size network as the base one. And then we also tried smaller networks, and we found that the same size network, which was larger, performed much better. So that's something I think we still need to investigate further.
Cool. So yeah, so thank you, Isaac. And let's move to the next presentation. And Ayush, the answer to your question B is yes.
All right. Hi, everyone. I'm Shannon, and I'll be presenting my group's project on mixed autonomy traffic control on behalf of my group mates, Ashay and Sid. So the setting we looked at was mixed autonomy. What that means is that we looked at traffic scenarios in which there were both AVs, autonomous vehicles, and human-driven vehicles sharing the same road and thus interacting with each other. More specifically, the environment we looked at was a bottleneck benchmark traffic scenario. So what that means is that we looked at a bottleneck in which 4 lanes of traffic merged into 2 lanes of traffic, merged into 1 lane of traffic, thus creating congestion. And this was benchmarked in previously released papers. People looked at the performance of RL algorithms like PPO for controlling the RL vehicles. So the states that people used to model this benchmark traffic input scenario was the number and average speed of vehicles in various segments of the benchmark, so both human and autonomous vehicles. And the actions that vehicles could take were to accelerate and decelerate as they moved through the bottleneck. We looked at both no lane changing and lane changing scenarios, but today I'll just be talking about no lane changing just to keep things under time. So more specifically, the RL vehicles were all modeled using single agent algorithms. So we trained them using PPO with GAE, and they all share the same controller. The human drivers aren't intelligent. They just try to follow the car in front of them with some given distance and some randomly generated acceleration noise. So the goal of previous papers was mostly to improve the average speed through the bottleneck to try to get rid of congestion that happened. What we decided to look at was how performance would be impacted that throughput would be impacted when explicitly considering some other factors. So the first factor we wanted to look at was fairness, because as you'll see in a minute, the previous solutions that the RL vehicles found were actually pretty unfair. And that had ramifications for both ethics and the acceptance of these RL vehicles onto the road. We also wanted to look at human driver variation. So previously the human drivers were all modeled using the same sort of model. And we wanted to see if training the RL algorithms with more variation in humans and how that would impact their performance. So looking at the importance of fairness, this video shows the policy that the RL vehicles learn when trained without any regard for fairness. So the red vehicles here are the RL vehicles, and you can see that what they do to try to maximize throughput through the average throughput through the bottleneck is to sort of create this stopper in the upper lanes to reserve this really high throughput capacity lower lane. But of course, you wouldn't really be happy driving behind an AV in the upper lanes. So how we tried to resolve this was we added an explicit fairness reward penalty, penalizing standard deviations across lane speeds in 2 segments of the bottleneck. So here where 4 lanes merge into 2 lanes, and then here as well, where 2 lanes merge into 1 lane. And we experimented with different combinations of these penalties. So just visually, after adding the penalties, you can see that the AVs learn a much different policy. So they learn a policy that sort of encourages an even distribution of speeds across the bottleneck lanes. Looking at the results in more numerical detail, we can also see that the standard deviation of speeds across lanes with the fairness policies penalties, as you would expect, are much lower than without the fairness penalties. Surprisingly though, the outflow and the throughput efficiency through the bottleneck, which were sort of the metrics used to measure performance previously, are also, while nominally maximal in the no fairness case, they're actually not that impacted by adding the fairness penalty. So even though the numbers are somewhat higher in the no fairness case, if you consider the range of standard deviations across rollouts, so we did 40 rollouts like the evaluation used in the benchmark paper, you can see that the values are actually comparable. To go really quickly over the multiple human drivers, how we approached that was to add different driver types that we randomly sampled parameters for, so maximum acceleration and following headway from distributions. And basically adding the human drivers didn't really change the outflow and throughput efficiency too much, but I think I'm out of time, so I'll stop there and open up for questions.
Any questions from anyone? No. So in the human driver experiment, you just had different models for every human driver. Is that what you were experimenting with?
Yeah, so in the no lane changing case, there's like not a lot of parameters to experiment with, but yeah, we chose we basically just added noise to those parameters and generated some different types of humans. There are quite a few more parameters for the lane changing experiments, but I just didn't talk about them. But those are things like driver aggressiveness for changing lanes, cooperativeness and stuff like that.
I see. And the fairness part of the talk was coming up with the reward function and tuning it challenging, or were you able to easily tune the reward function?
Yeah, so the reward function was actually, so I guess the thing that we need to tune the most is like the weights that we did to add the reward functions into the overall reward. So basically the first set of weights that we tried was just to get things on the scale of the other rewards, and just adding that like basically resulted in the behavior that you saw in the video. I think we could do some tuning on those just to see if we could get improved performance, but it wasn't a painful process.
Okay, sounds good. So if there are no other questions, let's thank the team. And I guess, maybe you can answer Ayush's question on the chat. So let's move to the next presentation.
Okay, hi everyone, I'm Siri. My final project is about learning to solve large-scale vehicle routing problems. So the vehicle routing problem, or VRP, is a NP-complete combinatorial optimization problem that have many real-world applications, such as in last-mile delivery or ride-hailing services. The formulation that we use is the standard capacitive vehicle routing problem, where we have a single depot and a set of customers in the 2D Euclidean plane. We assume that we have a vehicle with capacity C, and then the goal of the vehicle is to visit each customers as different routes, and the capacity constraint requires the sum of demands along each route to be less than or equal to C. The objective of this problem is to minimize the total traveling distances of all the routes. So there are a lot of work that try to solve this problem, both in terms of traditional operational research heuristic or learning-based methods. Traditional heuristics, they have very good solution quality, even on very large size problems, such as of size 2000, but they are very slow when the problem size are large. On the other hand, learning-based methods, they are fast, but they are inaccurate even on very small sizes, such as size 100. So in this project, we aim to combine the best of both worlds using a decomposition-based iterative pipeline. Our hypothesis is that we can approximate the large problem as a series of small subproblems to solve, so that we can both get good solution quality and good solution time. So our framework requires two components. One is a heuristic subsolver that only need to solve small subproblems. And then the other framework is a learning-based subproblem selection network that identifies good small subproblems for the heuristic subsolver to solve. However, without any restriction, the learning to select subproblem is very hard because there are exponential number of choices. So we use the spatial locality that commonly exists in combinatorial optimization to reduce the action space. So for example, in VRP, we know that customers that are close by in the Euclidean space are more likely to be clustered together in the same route than those that are far away. So in our pipeline, we basically reduce the subproblem selection space from exponential to linear in terms of the number of routes in the current solution. So we define each subproblem to be centered at the route and contain the k-nearest neighbor routes of the center route. And then the distance metric for k-nearest neighbor we use is the basic Euclidean distance. So given this linear number of subproblems, our neural network wants to select the best subproblem for the subsolver to solve, and then the iteration proceeds. So now the question becomes, how should we train the subproblem selection network? Like which subproblem is good? So we have the natural reward function that's defined by the immediate improvement that we can get if we can feed each subproblem to the subsolver. So ideally, we would like to select a sequence of subproblems that lead to the best total improvement after many steps. However, the subsolver takes non-trivial amount of time, making long horizon planning infeasible. So in this project, we restrict ourselves to consider the one-step immediate improvement, and we want to select the subproblem with the best immediate improvement. So we designed a graph neural network, a three-layer graph attention network to encode the problem. And our output is to try to fit the greedy expert. That is the expert that selects the best immediate subproblem with the best immediate improvement. And here are the results. We compare with the state-of-the-art VRP solver LKH3, and our method not only beats it in terms of solution quality a little bit, and it greatly reduces the solution time. We also compare our learning-based model with a few handcrafted heuristic selection model that we designed. And our model, the blue curve, outperforms all those heuristic models. Lastly, we check how good our model fits the greedy expert by deriving upper bound. So our training curve is a green curve, which is overestimated training curve due to a similar reason as in double DQN because of the noisy max that we take. So we derive a closer upper bound as the orange curve, and we see that our model fit the blue curve is very close to the orange curve for all three problem sets that we test on. So in summary, our decomposition-based pipeline is very effective in solving large-scale VRP problem. As future work, we want to try to plan with longer horizon by potentially deriving a faster model for the subsolver so that we can plan more quickly. And we also want to use some feature learning to select the subproblems, as currently we only use the 2D Euclidean distances as a metric for the KN, but that requires differentiable optimization as KN is non-differentiable. And that's it for the presentation.
Thank you. Any questions from anyone? So is the main bottleneck in going to longer horizon the fact that subsolver is very slow?
Yes, as you can see, the time for a size 2000 problem, it takes 12 minutes for 30 steps. So each step takes like 20 seconds or so, which is very slow.
I see, I see. So is your method now the new state of the art on this problem?
We think so, in terms of solution quality and solution time. But like the solution quality is like similar to the state of the art, but like our main contribution is the reduction in the solution time.
I see, I see. And in the graph neural network, were there any specific things you had to do, or was it a straightforward application of the graph network?
Yeah, we just use the graph attention network by design, by like specifying what node features and what the edges are. It's quite straightforward.
Okay, cool. So I guess if there are no more questions, let's thank Sirui and move to the next presentation.
Okay, good morning. So today we'll be looking at residual policy learning. So a large part of my project was to replicate the results of the RPL paper and then also to run it on some further environments with the aim of exploring the limits to find out what we can do with residual policy learning. So as a bit of a background, so we can perform sim to real domain transfer using some techniques we've seen before. So we're fairly familiar with domain randomization and system identification. So these are some common ways of doing domain transfer. But both of these strategies have sort of a limitation in that we need to have some prior knowledge of our environment parameters. So in the case of domain randomization, we need to know which of our parameters in, say, our simulation environment we want to be randomizing. And there's a similar issue with system identification. And this sort of becomes a bottleneck if we're trying to solve a task where we don't have access to this information, or if we're doing a type of transfer where the difference in the simulation and the real environments, or like I guess just any sort of the two environments that we're trying to transfer between, the difference can't really be expressed just in terms of environment parameters. So sort of the idea behind residual policy learning is to first train it in some source environment, and then improve the policy by training by continuing training in the real environment. And the objective is to hope that this pre-training in the simulation will reduce the will improve the sample efficiency in the target environment. So this is sort of the main idea behind the residual policy learning paper that came out a few years ago. So the idea was that we can use this sort of an idea to do transfer, especially for long horizon sparse reward tasks. And our goal in this project is to explore sort of the limits of what RPL can do. And so what we do is we reproduce these results, and we also additionally evaluate the algorithm on another range of tasks. Sort of as a summary on our results, in general, we find that RPL does improve the sample efficiency when running in the target domain. But there are also some surprising cases where it turns out that residual policy learning actually worsens the performance. But just before we talk about the results, I guess just sort of as just a recap on what residual policy learning does. So the idea is that we can suppose we have some sort of we have a simulation environment that is trained on some type of decision process. So we have, and the idea is that, well, so if we have also trained some policy pi that solves this simulation, then this induces a residual MDP with these transitions. So the idea is that we have the original policy, and then the actions that we make in this residual MDP are added to the policy that was trained in that we achieved in the original MDP. And the idea is that if our simulation is a close approximation for the real world, then the residual MDP might be a little bit easier for learning. So for some better intuition on what is happening there is an alternative equivalent formulation, which is that if we are given a policy in the simulation, then an optimal real world policy might be expressed in a similar way, in this way. So we have sort of the original policy from simulation plus some residual difference between the two policies, combining to give the optimal policy. And so the idea is that if our simulation is a close approximation, then this residual, this F can be interpreted as a bit of a corrective term. And so what we do when we're implementing RPL is that we first train the policy pi in simulation, and then in the real world we train to find the residual policy F in the residual MDP. So what we did was we try RPL in sparse reward goal-based environments. So we trained this with DDPG and hindsight experience replay to help us with the sparse reward for the goals. We also experiment to see what happens if we train with using PPO in a non-goal-based environment to see what residual policy learning can do for us. And we compare this against our baselines, which is if we do no transfer, which is when we directly use the simulation, the policy trained in simulation on the real environment. And also if we also compare to the sample efficiency we get if we train purely inside the real environment. And the environments we use, so we use PyBullet and Mojoko simulators to give us domain transfer. And we also test transfer across different physics parameters such as friction. So the first thing we did was we replicated the result from the original paper. So we used DDPG and HER on the fetch push environment. So and we did transfer with a different coefficient of friction. So we can sort of see this is on the original environment. The robot can just push the box across the target location. In a slippery environment, it also does that, although sometimes it can fail. So in this one, it throws the box off the pavement. But sort of the overall results we get is that we can see that
Jerry, we have about 30 seconds.
Okay, I will try to speed this up. But essentially, the results we see is that in this environment, we can see that our residual policy learning does improve the sample efficiency. I'm going to move a bit quickly. We trained this also with on an inverted double pendulum using PPO to see, and we find that here the residual policy learning result is it actually it performs not as well as purely just training in the real environment. So residual policy learning actually seems to make it worse. So we sort of propose a hypothesis here on try to explain sort of why this is happening, and we suggest that maybe it's because residual policy learning is most effective in environments where there is sort of a much clearer distinction between planning and execution. And I guess intuitively, the reason for this is that planning transfer is something that can transfer a lot easier than execution. And this is sort of a difference we can see in between the two environments we went through before as well. And so in terms of future work, it would also be interesting to investigate on an even larger range of environments, and also to compare between on-policy and off-policy algorithms, reward functions, as well as the importance of the planning factor in the environment and task. But yeah, so that's sort of, that's my presentation. So thank you, and I'll be happy to take any questions.
So unfortunately, we don't have time for questions. So let's move to the next presentation, but thanks, Jerry. Well, I guess you can answer question in the chat.
All right, hey everyone. So this is our presentation on fine-tuning a conversational chatbot using reinforcement learning. And so just to give an overview of the problem statement. So supervised learning can work quite well to create conversational chatbots, but one challenge that frequently comes up is that the bots will either repeat themselves a lot, or they'll run into roadblocks where they'll say things like, I don't know what you mean, or I'm not sure what you mean. And we call these kind of dull responses. And so one thing we're trying to do is take a supervised chatbot and make it better and train it to not get stuck in these feedback loops using reinforcement learning. The other thing that's an interesting challenge about this project is that, so these aren't goal-oriented chatbots, they're just conversational. The goal is just to have a high-quality conversation. And so as we'll touch on shortly, designing the reward function gets tricky because it's hard to quantify exactly what makes a good conversation. And so moving forward, what we're doing is first we use supervised learning to train some chatbots. And so we tested a couple of different things, fine-tuning some pre-trained models and training one from scratch. And that is just trained based on the supervised training data. And so the examples we'll show later are of a chatbot that was trained using a data set on conversations about movies. So you'll see some of the examples. The chatbot likes to talk about movies a lot. And then we go on and we do reinforcement learning and we give it a reward for high quality conversations. We're using vanilla policy gradients as sort of a first step and first attempt at doing this. And so going forward, the reward function, so we are more or less replicating an example paper. And so we use the way that they've outlined their reward function as well. And so there's three different components of the reward function. So first there's ease of answering. And so we hard code some example dull responses that we frequently see in the supervised chatbot. So that's like, I don't know, or I'm not sure what you mean. And then we penalize the log probability of a response generating that reply, generating a dull response as a reply. So if a sentence is likely to get a dull response as a reply, that incurs a negative penalty. We also have an information flow penalty, so that's avoiding repetition. So we penalize the cosine similarity between the statement and the previous statement. And then we have this semantic coherence penalty, so we also have a backwards model that predicts the previous sentence based on the current sentence. And so we have that reward for that as well. So basically that is necessary to make sure that we have sentences that have a high probability of being predicted by that backwards model, so that we still have sentences that make sense and work with the flow of conversation. If you just had those first two penalties without the semantic coherence penalty, you start to get some crazy results, as we'll show later. So that's the reward function, and then I'll pass it to Simon.
So now to give you a bit of a overview on like the structure we use to train the model. So basically what we've done is instantiate two different agents. One, which is the supervised train agent, which as Stephanie discussed before, could be GPT or like any sec-to-sec model. And then like a pre-train, and then another instance, which is our oral agent. And what is important to understand is the fact that we're not touching or training any of the like first agent, but only using vanilla policy gradients to optimize the answer generated by the oral agent. And the way the pipeline is working is we'll start with like a prompt statement. Then the oral agent is going to reply. This is going to make a state, which is the previous statement and the current statement, and we're going to calculate our reward and policy. And then the environment agent is going to reply and keep iterating until we decide to terminate the episode, calculate the loss and the policy loss, and iterate until we get the oral agent to learn. so the results, from the reward function is very similar to what is in the paper. So as Stephanie described before, the action space is very large and it's very hard to get, an ideal converging reward. However, what we had for the training amount we've done is, kind of similar to what has been demonstrated in the paper. And as we're going to see after, the results are actually improving. So here are some examples of chatbot conversations. I think the first one in blue is probably the one which is the most eloquent. So you see that before the RL, the GPT really gets stuck in an I didn't like loop, which is pretty dull and can't move out of it. And once we add the RL training, it actually managed to have like much more meaningful and much more conversation, which actually flows until we decide to stop it. And same, not as obvious, but if we look also at the second conversation in gray, you see that, the quality of the response, for instance, like the last one, has repetition, like the suspense and, these kind of things, or also kind of improved, with the oral agents. And just to maybe kind of come back to what Stephanie was discussing about the importance of the semantic coherence reward. So, these are some examples of, what we had before adding this reward. And, we saw that, when trying to backpropagate our like policy loss and modifying the model, we will lose, it will actually modify a lot of the model to the point that it doesn't make any linguistic sense anymore. So this was, very interesting to see how it affects the stability and preserving the quality and the coherence of what the chatbot was saying. So yeah, this is all from our side. Any questions?
No questions. So what do you think is the problem with the current system? Is it having long-term conversations? Is that still an issue?
So, I think, something which is a bit hard is, even though this reward kind of guarantees the flow, if you think about the overall goal of it, having something which really sound like a human and, doesn't, now for instance, we fine tune the data set on open subtitles, which is, very movie oriented sentences. So, it kind of sometimes still gets stuck to, it wants to talk about certain things and, it might not sound like as natural as possible. So, I think you have two aspects to consider. I think the RL can help with the flow, but, something which needs to be improved if you want to have something which sounds really like a human is also, improve the linguistic model itself. So, yeah, that's kind of the two things we could like work on the future moving forward.
Okay, well, thanks a lot for your presentation. So with that, I think we have come to the end of the course. So, thanks everyone who came to the class. I hope you found it useful. If you have any feedback on the class and how the class could be improved or anything that you would like to say, I think there is a MIT-wide survey which is open till 24th of May. So I definitely and highly encourage you to fill out that survey. And I think your project reports are due at the end of the week. So looking forward to all of your project reports. So our grades are due on Monday and we'll be submitting the grades on Monday. So we don't really have much flexibility with the timeline. So it would be great if you you stick to the timelines that we suggested. So with that, if there are no more comments or questions, we'll officially close the class. And best of luck. And maybe one day or sometime soon you'll find an opportunity to apply reinforcement learning for either a job that you end up doing, or maybe starting your startup, or maybe in your research.